Hello, Physics 2 people. Um, in this video, I want to talk about the energy stored in an inductor. Um, so what I want you to think about is a solenoid. So let's imagine. And I want you to imagine that initially there was no current flowing, and then you increase the current by adding more and more current until eventually you have a pretty considerable current flowing through the wire. When you do that, um, you know, there's an EMF, so there's work that's being done as the current crosses the inductor. In particular, you could say that the work being done per charge, or sorry, the work being done is simply going to be the EMF with up to a minus sign times dq, because the EMF is minus the work per charge. On the other hand, the EMF can be written as d phi, the rate of change of magnetic flux, which can be written as minus L times di dt times dq, or kind of playing around with some differentials, we can write this as minus L times di dt times dq dt t. And finally, being a little cute here with the differentials, I can write that as minus L. I can think of this as I, and then I can cancel this differential with this differential, and I can think of it as I times di. Very good. So rewrite this on the next line. So the work done building up this current is minus L times I di. Okay, so that's as you build up the current, you would get that. On the other hand, if you were to decrease that current, then the you would get the same magnitude work out. You just reverse the direction. So, but the fact that the energy is returned to you means you can think of a potential energy. So we could actually just say the potential energy stored in the inductor is, well, it's positive. It is minus the work. So that's just going to be positive LIDI. So as we start with no current and we gradually build up the current, you can imagine you are storing potential energy in the inductor. Integrating both sides gives me that the magnetic field stored in inductor is 1/2 L times I squared. Okay, so that's a kind of a formula. This is very similar to a formula we had for capacitors, and that was that the potential energy in a capacitor was 1/2 to think about for 1 second. So it was 1/2 Q squared divided by C, the capacitance. Very similar kind of formula. All right. So what we want to do is, just like we did for the electric field result, we want to rewrite this in terms of um, magnetic field quantities. To do that, we remember that the magnetic field for an inductor, for an infinite solenoid, is mu naught in I divided by the length of the solenoid, which means I can turn that around to say the current is L times B over mu naught in just checking my details. Right. So I can write the energy stored in the inductor as 1/2, and the answer has L times I squared, which I can write as 1/2 and we can write that as L I right. It's okay. I'm sorry. I'm just checking my little factors. Um, Li squared. So I could write that as, oh dear, too many factors of L. This is the length of the solenoid. Length of the solenoid. There we go. Now I apologize. It's getting late. And this would be the length of the solenoid times B squared divided by mu naught squared times N squared. On the other hand, the inductance for an infinite solenoid equaled mu naught times N squared times the area of the solenoid divided by the length of it. So this becomes 1/2, plugging in for the inductance, I get mu naught N squared area divided by L times L B squared over mu naught squared N squared, and canceling out it most of the stuff. That cancels. That cancels. hold on. It's I squared, so this should have been L squared. So that should have been L. The denominator fully cancels and you have one factor of L left over upstairs. This cancels one of these. So writing our final answer, we get 1/2 B squared over mu naught times the area times the length of the solenoid. This is nothing other than the volume of the solenoid. So we can define an energy density, B, which is the energy divided by the volume. We find that for the magnetic field, the energy density goes like B squared over 2 mu naught. That's the energy per unit volume in a magnetic field. That should look pretty familiar. You might remember that we had a similar sort of energy density for electric fields, which looked like epsilon naught E squared over 2. So the coefficients up, the constants upstairs in that expression, but it's very similar type expression. As we've found many times, there's a definite parallel structure between the electric and magnetic fields. All right. So that's the result telling us inside an inductor that's, where the current is fully built up, how much energy is stored and can be returned to the circuit if the at a later time. Okay, so that is a wrap on inductors and inductance and magnetic materials and solenoids. And we're bringing the semester to a rapid completion here. The final topic we have to discuss this semester is a discussion of Maxwell's equations, which so kind of bring the whole subject of electricity and magnetism together into one place, and also as a kind of a byproduct of that, we will learn about electromagnetic radiation and light. So we'll see. It's, to me, it's the most interesting, kind of the most I don't know, the most interesting and maybe in the kind of the most profound part of the course. So hopefully you also enjoy it. All right, see you next time.